In today's video, we'll be going over how to set up and solve the question on test 3. The objective for this question will be that I can use Faraday's law to calculate the EMF associated with the electric field. Now, let's look at the question. Voldemort needs to induce a current in a single variable area loop to power his latest spell. The area of the loop changes with time according to the plot below right. The geometry and orientation of the situation is shown to the below left. If the loop is placed in a constant 15 Tesla magnetic field, what is the potential difference around the loop, and in what direction is any induced current flowing at t equals 1 second and b equals 4 seconds? Now, let's go over how to solve this. First thing, as stated earlier, you're going to need to know Faraday's law, which states that the EMF is equal to the negative, which is very important to know, negative derivative of the magnetic flux with respect to time. For our problem, we have a constant magnetic field, so we know that that is 15. We know that A is a time-dependent area, so we can write that as A is a function of t. And also we know that the EMF is equal to a delta V in this case, or the potential difference since there's no resistance, and that the slope of the non-zero sloped line in the plot is -4/3. Now, the most important part in this question is how to set it up. So first off, we take our Faraday's law equation, and let's simplify it a little bit. So we'll take that EMF is equal to the derivative of the flux, or we can rewrite that as B dot A. And in this case, since B is a constant, we can take that B out. So then we get the EMF is equal to the negative B times the derivative of A with respect to t. Now, luckily for us, we actually have an A versus t graph already plotted for us, so we can just take values from that table. So, therefore, that means that at t equals 1 second, and we look at our graph, A equals 4, which, plugging into our equation, we get -15 Tesla times 4 meters squared, which gets us a EMF of -60 volts, which is equal to a potential difference of -60. Now, to find the direction of the current, you just use the right-hand rule, and you take your hand and you point your thumb in direction of the magnetic field, and then your hands curl and make it seem like it's actually going counterclockwise initially, but then you have to account for the negative sign, so you flip your hand around, and your fingers curl in the clockwise direction, so the current is flowing clockwise. We can do the same thing for the time 4, but this time we don't exactly know A, but we can figure it out pretty simply by just doing a simple slope conversion. So we know that the slope of the entire linear line is -4/3. So since it's linear, we know that the same thing can be said about this little section right here, which the y value will give us our A at time 4. So we can see that -4/3 is equal to -A over 1, and that gets us A is equal to 1.333 repeating. So, same thing as we did last time, we just plug it into our derived equation, which now gets us -15 times 1.33 repeating. The EMF is equal to -20 volts, which means that the potential difference is equal to -20 volts. And since it's the same sign as last time, we know that it's clockwise, but again, you can use the right-hand rule if you want to make sure. Point your finger in that direction. Since it's negative, you got to flip the sign, and you're pointing in the right direction, which would be clockwise.